Proxima Centauri, the closest star to us, lies 4.2 light-years from Earth, a vast distance that takes an immense amount of time to cross. If we are to leave the solar system, we must confront two major challenges. First, the speed achievable with current technology, chemical rockets, is simply not enough. Second, the energy required would have to be thousands of times greater just to overcome the sun's immense gravitational pull. Research into ion engines, nuclear fusion propulsion, and bold ideas such as warp drives that could bend space-time in the future is gradually moving forward. However, these technologies remain only the first steps of a long journey, still facing countless physical and engineering barriers. And if one day we truly achieve this, could humanity evolve to adapt to the harsh conditions of outer space? Behind these questions about technology lies something far greater. Let us look toward a future where we may come closer to what once seemed impossible. The solar system is encased within protective, invisible bubbles. These are the heliosphere and its outer edge, the heliopause. The heliosphere is the vast region where the solar wind interacts with the thin gas and particles of interstellar space, forming a protective shield around our planetary system. The heliopause marks the ultimate boundary of the sun's influence, the point where the solar wind's pressure fades, no longer strong enough to overcome the push of the interstellar medium. NASA's Voyager 1 and 2 probes delivered astonishing insights into these remote frontiers. When Voyager 1 crossed the heliopause in 2012, it entered a region far denser with plasma than scientists had predicted, where powerful interstellar magnetic fields pressed back against the heliosphere. Later, Voyager 2 revealed that this edge is not a smooth boundary, but a turbulent, dynamic transition zone. These discoveries not only transformed our understanding of the solar system, but also underscored the immense challenge of breaching this invisible wall. Beyond the heliosphere lies the Kuiper Belt and the enigmatic Oort cloud, which redefine the true scale of our solar system within the Milky Way. The Kuiper Belt, located beyond Neptune's orbit, is a vast expanse filled with billions of icy bodies, the birthplace of many short-period comets. Here, distances between objects are staggering, highlighting the incredible stretches that even light must traverse. It takes about 5 hours for sunlight to reach the Kuiper Belt's edge. Farther still, on the outermost rim, drifts the Oort cloud. A colossal, spherical shell of trillions of frozen objects and rocky fragments, believed to be the source of long-period comets. It may extend to nearly a quarter of the distance to the nearest star. Meaning light from the sun would require thousands of years to cross it and thousands of years to reach the Oort cloud. Exploring the Kuiper Belt and the Oort cloud is more than a scientific endeavor. It is an active perspective, placing the true scale of our solar system against the vast backdrop of the Milky Way. Yet the sheer distance to the Oort cloud's edge illustrates the staggering challenge ahead. A journey beyond this frontier would demand unimaginable energy and time, far beyond the capabilities of our current technology. This boundary is not just a physical barrier, it is an invitation, a silent call to explore the unknown. Once we grasp the invisible boundaries of our solar system, the next question emerges. Just how vast is it really? To comprehend its scale, we must first consider the distances between its planets. From our small Earth to the massive Jupiter is already an enormous journey. But to reach the edge of the Oort cloud, that distance stretches into something almost unimaginable. The closest star to us, Proxima Centauri, lies only 4.2 light-years away, and yet, in reality, the numbers are staggering. Voyager 1, traveling at a breathtaking speed by human standards, would need about 75,000 years to get there. That's longer than the entire span of human civilization. The problem of time is not merely a matter of physics, it's a profound concept that shapes our perception of reality. Can humanity afford to wait thousands of years to witness the results of interstellar exploration? Time is not just a constant flow, it bends, it warps depending on motion. According to Einstein's theory of time dilation, as an object approaches the speed of light, time slows relative to everything else. This opens an extraordinary possibility. If we develop technology capable of near light-speed travel, could human experience of time transform entirely? Perhaps in the future, as technology advances, we will discover ways to overcome these immense distances, turning dreams of interstellar exploration into reality. But to achieve that, we must first confront the challenge of time itself, an inescapable factor intertwined with humanity's quest to conquer the cosmos. To embark on an interstellar journey, a spacecraft must overcome gravitational forces, first of its home planet and ultimately of the Sun itself. This requires achieving a specific change in velocity known as delta V. For Earth, the delta V needed to break free from the Sun's gravitational grip is staggering. It demands an almost unimaginable amount of energy to accelerate a spacecraft of any significant mass to such speeds. Here lies the greatest limitation of current technology: chemical rockets. These engines, while powerful enough to take humans to the moon and send probes across our solar system, are extremely inefficient. They lack the thrust and energy capacity to sustain long-during missions beyond the confines of our stellar neighborhood. To overcome this barrier, scientists are pursuing advanced propulsion systems, ion engines, nuclear fusion drives, and even the speculative warp drive. Ion engines, which use plasma to generate a steady, gentle thrust, are far more efficient than chemical rockets. Yet their low thrust means they are suitable only for missions within the solar system, not for achieving interstellar speeds within a human lifetime. A more promising, yet highly challenging solution lies in nuclear fusion propulsion. This technology seeks to replicate the process, powering the sun, fusing light atoms to unleash colossal energy. If realized, it could deliver unprecedented propulsion, enabling spacecraft to reach extraordinary velocities. But here's the catch. Controlling fusion for clean energy on Earth remains one of science's greatest hurdles. Miniaturizing it for a spacecraft engine is an even greater feat. And then there is the boldest concept of all, warp drive, a theoretical engine that would bend space-time around a spacecraft, allowing faster-than-light travel without breaking the laws of physics. In the meantime, spacecraft have relied on a clever workaround, gravity assist. By harnessing a planet's gravitational pull, probes like NASA's Voyager gain speed without expending extra fuel, slingshotting past Jupiter to accelerate on their journey. Yet even this ingenious maneuver only adds a few kilometers per second, nowhere near what's needed for interstellar flight. The interstellar medium is a vast expanse filled with unseen dangers. Once we leave the protective bubble of the heliosphere, spacecraft and any humans aboard will face a relentless storm of cosmic radiation and high-energy particles, primarily protons and heavy nuclei. These particles can pierce spacecraft hulls, inflicting severe damage on electronics and, more critically, on human health. They can alter DNA, raise cancer risks, impair cognition, and even lead to death. A striking example is Voyager 1, which encountered magnetic field conditions it had never experienced before as it exited the solar system. Add to that the extreme cold of interstellar space, and the challenge grows. Developing shielding effective enough to protect both machines and humans without adding prohibitive mass is an immense engineering hurdle. Interstellar space is also strewn with tenuous clouds of gas and dust. While their density is low, at interstellar speeds, even a tiny dust particle becomes a hypersonic bullet, capable of tearing through a spacecraft's hull. Protecting against these high-velocity impacts demands entirely new material designs. Ones that can self-heal or withstand catastrophic shocks. Another formidable, yet less obvious, barrier is communication. Light and radio waves travel at finite speeds. The farther a spacecraft ventures, the longer it takes for signals to reach it and return. To the nearest star, Proxima Centauri, a radio message would take over 4 years to arrive. Creating an enormous delay in command and data transmission. Maintaining reliable communication across such distances while combating interference and signal loss remains a puzzle without a clear solution. All these elements combine to make interstellar space a domain where invisible barriers are not merely technical challenges, they are matters of survival. To conquer this realm, we will need more than powerful engines. We will require materials never before created, unprecedented shielding systems, and the adaptability of human beings to endure the harshest extremes of the cosmos. Scientists are relentlessly pushing the boundaries of technology, driven by the hope of unlocking the door to unimaginable adventures into deep space. One of the most ambitious concepts is Breakthrough Starshot, a bold vision for a fleet of thousands of tiny spacecraft. Each weighing just a few grams, equipped with enormous light sails. The plan: fire powerful laser beams from Earth to accelerate these sails to astonishing speeds, up to 20% of the speed of light. At that velocity, a nanocraft could reach Proxima Centauri in just 20 years, carrying cameras and sensors to transmit data back home. Enormous engineering challenges remain, from building lasers powerful enough to sustain such acceleration, to stabilizing the sails, to ensuring communication across such vast distances. Yet this project proves that humanity is beginning to think beyond the confines of traditional rockets. Even further into the realm of science fiction are concepts like warp drives and wormholes. Alcubierre's warp drive remains an elegant hypothesis, bending space-time to allow faster-than-light travel without breaking local physical laws. Wormholes, on the other hand, propose shortcuts through space-time, tunnels that could link two distant points in the cosmos. For now, both require physical conditions never observed and exist only within the realm of theoretical physics. Space agencies like NASA, ESA, and JAXA, together with private pioneers like SpaceX, are joining forces to push the limits of human capability. Sharing knowledge, pooling resources, and uniting under a common vision will be essential, because interstellar travel is not the ambition of one nation, the collective dream of humankind. Among the boldest concepts in interstellar travel is the generation ship. More than just a vessel, it represents a profound symbol of hope and humanity's unyielding desire to uncover the mysteries of the cosmos. This idea stems from a harsh reality. Even journeys to the nearest star systems, such as Alpha Centauri, could take decades or even centuries. A generation ship would therefore need to sustain life for multiple generations, creating a self-contained world capable of supporting an entire society on a voyage across the stars. One of the greatest challenges lies in maintaining a stable, closed-loop ecosystem within the confines of a spacecraft. Scientists are exploring systems where water, air, and food can be recycled and regenerated using only onboard resources. Projects like Biosphere 2, an ecological experiment in Arizona, offer a glimpse into this challenge. A miniature world where air, water, and food had to be continually renewed without any external input. Ensuring resource sustainability, managing waste, and resolving technical failures over hundreds or thousands of years is a problem with no precedent. A single error could trigger catastrophic consequences. Energy systems represent another critical component. Nuclear power, solar energy, and even nuclear fusion, the very process that powers the stars, are being considered as potential sources to sustain such long-term missions. Fusion, if mastered, could provide an abundant and virtually limitless energy supply, drastically reducing reliance on conventional fuels and ensuring the viability of these epic journeys. Yet perhaps the most formidable challenges are not technological, but psychological and social. Isolation, confinement, and the intricate dynamics of a tightly knit community in an artificial world will test human endurance in ways we can barely imagine. What happens when generations live and die without ever seeing a real night sky or feeling the wind on their faces? How will humanity cope with monotony, cultural drift, and the inevitability of interpersonal conflict? Over time, will the original mission retain its meaning, or will it fade, distorted by the pressures of survival? Research into group psychology under extreme conditions, such as Antarctic expeditions and short-duration space missions, offers crucial insights. Ultimately, the dream of a generation ship is not just a feat of engineering. It is a journey into the deepest questions of who we are, what we value, and how far we are willing to go to claim our place among the stars. This is the point where we approach an entirely new frontier, the place where biology meets technology. Will humanity evolve to adapt or transform completely to survive? Evolution is a natural process that unfolds over millions of years. Yet in the context of deep space travel, that timeline could be forced to accelerate. Research suggests that humans possess the genetic flexibility to adapt to environmental changes. For instance, people living in high-altitude regions often develop physiological traits such as larger lungs for more efficient oxygen absorption. Similarly, if humans were to live in environments with high radiation or low gravity, new genetic traits could emerge to aid survival. One of the greatest threats in deep space is cosmic radiation, a relentless force that can damage DNA, causing disease and functional decline. To counter this, the idea of genetic engineering to enhance radiation resistance has entered serious discussion. Imagine a generation of astronauts genetically modified for superior cellular repair, cancer resistance, or even skin and organs capable of withstanding intense radiation. This is no longer pure science fiction. Technologies like CRISPR to Cas9 are opening unprecedented doors to altering the human genome. Living in low-gravity environments poses another major challenge. Studies on astronauts show that prolonged weightlessness leads to muscle atrophy and bone density loss. Over time, this could drive the evolution of lighter skeletons, bones strong enough to function but adapted for minimal gravitational pull. Beyond biology lies an even more radical possibility: the fusion of man and machine. If the organic body proves too fragile against the extremes of space, why not replace it? Cyborgs, half human, half machine, could endure radiation, extreme temperatures, and the vacuum of space in ways biological organisms never could. Imagine a human brain integrated into a robust mechanical body, or even merged into a fully synthetic AI system. And if artificial intelligence becomes so advanced that it develops consciousness and self-improvement, could AI become the ultimate successor for interstellar exploration? Machines do not fear radiation, require no oxygen, food, or water, and could function flawlessly for millions of years. They might be the perfect astronauts for journeys spanning eternity. But then comes the haunting question. If we alter our genes beyond recognition, if we abandon flesh for steel, what remains of our humanity? The definition of identity, consciousness, and purpose will be pushed to the brink. The voyage beyond the solar system may not just be a quest for new worlds. It could become a profound journey to rediscover who we are and whether we are willing to surrender parts of our essence to achieve the impossible. Interstellar travel is not a matter of the next few centuries. The barriers, physical, technical, and even biological and social, stand tall before us. Solutions like the generation ship or altering human nature pose profound ethical and philosophical challenges that humanity must confront. Yet, it is this very dream, the dream of pushing beyond known limits, reaching distant stars, that defines what it means to be human. It symbolizes our innate thirst for discovery, understanding, and transcending ourselves. Since the dawn of civilization, humans have always looked up at the mysterious night sky, wondering about their place in the vast universe. It is this relentless curiosity that has driven us to develop science, technology, and philosophy. Space exploration, in a deeper sense, is a journey of self-discovery. Whether or not we truly leave the solar system in the next few millennia, the quest for answers fuels our strongest motivation, pushing us to grow, to dream, and to strive endlessly. Perhaps in this unending journey, we will find deeper meaning in our existence within this mysterious cosmos. for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.